Assalamualaikum and a very good morning to Madam and everyone. We are from Group 5. My name is Afiqah Binti Ahmad Azli and my members name Siti, Nuriffah and Esraa Alaaedin. Today I will be present about my electric circuit 2 project, which is this project focused on simulating a second order RLC circuit response using MATLAB Simulink. The apps that my group is using is MATLAB Simulink. The main objective is to analyze how different resistor values affect the system behavior, whether it becomes overdamped, critical damped, or underdamped, and compare the summation with the manual calculation that we already calculate. Okay, first thing, circuit that we're gonna simulate is a circuit overdamp. We're gonna see the waveform of overdamp and a value of overdamp value and the simulation and manual calculation. First, as you can see, this is the original circuit from the question, but as you can see here, control voltage source, the original are not using a control voltage source. There's a normal voltage source, but here in Simulink MATLAB using control voltage source is because this block converts a Simulink signal into a physical voltage in the SimScape MATLAB it allowed us to apply a custom voltage input to RLC network, so it can display on the value and scope, which is scope is used to visualize how a current and voltage change over time during the simulation, and it will come out the waveform. Next is current sensor. I put within a resistor and inductor, which is current sensor is a block measure that current flowing through the circuit. It converts the physical current into a Simulink signal, which can be connected to display on scope. It's the same as a voltage sensor. Measure the voltage across by 2 points in the SimScape circuit. It also converts the voltage into a signal for Simulink, which is voltage sensor. I put in across the inductor so it can match the value of inductor. Then the solver configuration is the thing that you need to put when you do a circuit in a MATLAB Simulink, which is solver configuration block is required in every SimScape physical network. It defines how Simulink solves the system of equation in the background. Without it, the simulation cannot run because the solver won't know how to handle the physical component. So solver configuration is a main thing to circuit in the MATLAB Simulink. Then is a step block, which is step block is used to provide a sudden voltage input from 0 to a desired value at a specific time, simulating a switching action. Is connected to control voltage source to simulate during on the power at T0. For them is I change the value of resistor. Capacitor is using our value ohm is I'm using 0.5 microfarad, and resistor will be 800 ohms while keeping the inductor and capacitor values the same. The higher resistance slows down the current decay and prevents any acceleration. Okay, the circuit connection remains similar, using a current sensor and a voltage sensor to observe the system response. The simulation was run up to 0.15 seconds to give enough time for the slow decay to appear. At the end of the simulation, the current display was 0.06233 ampere, and the voltage across the inductor was 1.987 volt. This small value shows that the system is reaching steady state slowly, and there was no overshoot or acceleration in the waveform. This result matched the expected behavior of an overdamped response. Okay, next for critically damped. For the next after overdamp, which is we just change the resistor value, which is capacitor, inductor, and the one resistor that we follow the same value as equation, and we change the stop time to see the waveform critically damped, which is resistor value is set to 400 ohms to achieve a critical damp condition. I also added a current sensor at the beginning of the circuit to measure current IT and a voltage sensor across the inductor to measure VLT. The stop time was set to 0.05 seconds here. Because created dam system stabilized quickly, this setup allows me to observe the behavior of the circuit in a short time interval after the input is applied. Okay, lastly, I test the under dam condition by reducing the resistor value of 100 ohms. This low resistance caused the system of oscillate before settling down. The same RLC circuit configuration was used, and I ran the simulation with this stop time of 0.1 second to capture the full oscillation behavior. So the waveform clearly slowly bringing oscillation that delay over time. The current at 0.1 second was 0.1392 ampere, and the voltage across the inductor was 5.414 voltage. This value reflects that the energy continues to exchange between the inductor and capacitor.
For question 2, the simulation is based on a different type of circuit. This time I use an AC circuit source connected in parallel with two resistors and a capacitor. The objective is to analyze the voltage across one of the resistors using nodal analysis and compare the simulation result with manual phasor calculation. The simulation used an AC current source with a sine wave, and I measure the voltage at a specific node using a voltage sensor. I set the simulation stop time to 1 cycle based on the frequency of the source. The results show a voltage of insert actual value if need at the selected node. However, the simulated voltage was not exactly the same as the manual calculation. This is because the manual method used phasor analysis in steady state, where the simulation is done in the time domain. The AC current source continuously varies over time, which causes slight difference between the two results. But overall, the simulation waveform shape and behavior still reflect the characteristically response.
Assalamu alaikum, doctor. My name is Esraa Alaaedin AbdelRahim. My matric number is BEJ10403. For our project, I will present the last part, which is conclusion. In conclusion, this project helps us to understand how the different value of the resistance affects the RLC circuit through simulation or a manual calculation. For the result of the overdamping, critically damping, and underdamping condition matches the expected response patterns. For question 2, the sinusoidal steady-state analysis using both nodal and phasor method, also a legend with a simulation trend. Finally, this project helped us to improve our understanding for both time domain and AC steady-state analysis. That is all for our project. Thank you.